Hello, in this video I'm going to solve some examples on power series lecture 15. I will solve some of the problems in the assignment 9 to review this lecture. So these 4 steps I have copied from the lecture notes is the main thing we need to do in solving these kinds of questions regarding power series. We want to find the interval of convergence. We use ratio test. We do find the interval. Anything inside that interval converges. Anything outside that interval given by the ratio test diverges. But we are not sure about the endpoints. So we are going to test the endpoints individually. So we have 2 series, one in the right side of the interval, one is in the left side of the interval. We are going to test these 2 points manually using different techniques we have learned, and then we can find the interval of convergence. So I'm going to just practice this in questions on power series. So the question in the assignment says find the series radius. So we know if we have a center, the distance from the center to the right side of the interval or left side of the interval is the radius of the interval. And also the question asks for what values of x does the series converge, absolutely or conditionally. So again, this is very easy. Anything given by ratio test converges absolutely. That was one of the main results of the ratio test. It gives us absolute convergence. And for conditionally, it might be only in the 2 endpoints of the interval, which we are going to check. Just a quick review. Conditional convergence is related to a series which converges, but the sum of its absolute values do not converge. So I'm going to show these in different examples. Let's start with question 2 in the assignment 9. We have a series n from 0 to infinity of x plus 5 to the power of n. So start with ratio test. We find the limit of un plus 1 over un. So for the next examples, I'm going to avoid writing this first part. It's the same thing for all examples. I don't write limit of un plus 1 over un. I just write the result. We want this to be less than 1. Un plus 1 is x plus 5 to the power of n plus 1. And un is x plus 5 to the power of n. We want this to be less than 1. Very easily we can see it means that the absolute value of x plus 5 should be less than 1. Why? Because this is cancelled, this is cancelled, and this is reduced to x plus 5. In case it's not clear, because we can write this as x plus 5 over times x plus 5 to the power of n, and then this is cancelled with the denominator, x plus 5 is left. Okay, when the absolute value of x plus 5 is less than 1, it means x plus 5 is between 1 and negative 1, or x is between negative 6 and negative 4. So we found the interval. We know in what interval the series is converging. The radius is obviously 2 because the distance from -6 to -4 is 2, so the radius is 1. In other words, we are divergent from negative 5 to negative 4 and negative 6. So you can see this is the interval, and then the radius of interval is 1. Now we should check these 2 points, -4 and -6. We don't know what happens at these endpoints, but we have the interval of convergence between -6 and -4, and in this interval we are sure that it converges absolutely, because it's the result of a ratio test which gives us absolute convergence. But we should check -4 and -6 too. So we don't know what's happening to the series at these 2 points. So let's test it. At x equals -6, what do we have? Let's look at the series here. At -6 we have sigma n equals 0 to infinity -1 to the power of n. We have discussed this series previously. This is something like this. It's -1 to the power of 0, which is 1, -1 to the power of 1, -1, 1, -1. So we discussed this. It's divergent. It's not converging to any number. In class I proved that this is not converging to any number. Let's see what happens at -4. At -4 we have, again, if you look at the original series, we have -4 plus 5, which is 1. So 1 to the power of n, it's 1 plus 1 plus 1. Obviously divergent. So at 4 and as -4 and -6, the series is divergent. We have absolute convergence at this interval, and we don't have conditional convergence anywhere, because at -4 and -6 it's diverging. Above -4 it's diverging too. Below -6 is diverging too. So we have absolute convergence in this interval with the radius 1 and center of -5, and at any other points in this interval it's converging absolutely. Outside of this interval it's diverging. I know I repeated it many times because it was the first example. The next example I will go faster. The next example I'm going to solve is question 4 from the assignment. Sigma from 1 to infinity 3x minus 2 to the power of n over n. Quickly we do the ratio test. You can see the ratio test is the limit of an plus 1 over an, or un plus 1 over un. If you write the values, I skipped the first step, you can see we have 3x minus 2 to the power of n divided by n plus 1, obviously, divided by 3x minus 2 to the power of n, and then we have n over n plus 1. So here this gets cancelled, and what's remaining is 3x minus 2, and obviously we have an absolute value which we should be careful. So absolute value of 3x minus 2 times the limit of n over n plus 1. We have talked about this limit a lot. We would just want this to be less than 1, right? So the limit of n over n plus 1 when n goes to infinity is 1. Therefore this whole thing, the whole limit is less than 1 when the absolute value of 3x minus 2 is less than 1, because this thing is 1 when n is big, so we don't need to worry about that. I we have this inequality, same as before. 3x minus 2 is between 1 and negative 1. Let's add all sides by 2. So minus 1 plus 2 is 1. 3x minus 2 plus 2 is 3x, and 1 plus 2 is 3. Therefore, we can divide this by 3 because I want to have x here in the middle, so I divide everything by 3. We have 1 over 3 divided by x. This is less than 1. Okay, we have the interval. Obviously, the radius of the interval is 1 over 3. Why? Because we have 1 over 3, 1, and the middle is 2 over 3. So the radius here is 1 over 3. We just need to check these 2 points. Let's start at 1 over 3. We are going to replace 1 over 3 in the original thing. So 1 here. 1 over 3 times 3 is 1, minus 2 we have negative 1. So the series at 1 over 3, we have the series of negative 1 to the power of n over n. N is changing from 1 to infinity. Again, I repeat how I got negative 1 to the power of n. Here, replace this x with 1 over 3. 1 over 3 times 3 is 1, minus 2 we get negative 1. Okay, what is this series? You have seen it before. It's alternating harmonic series, and it's conditionally converging. So this is converging, the absolute value is not. So at this point we have conditionally convergent series. This is alternating harmonic series, which we have discussed in the previous lectures. So we should check x equals 1. We checked x equals 1 over 3. At x equals 1, let's see what we have. We have 1 times 3 is 3, minus 2 is 1. We have 1 to the power of n, which is 1 over n. Again, we have discussed this a lot. This is a diverging or divergent harmonic series. So the interval of convergence is this. At 1 over 3 it's converging, at 1 it's not converging. The radius is 1 over 3. At all points between 1 over 3 and 1, the series is absolutely convergent. At this specific point of 1 over 3 it's not absolutely convergent, it's conditionally convergent. Next example is, let me solve question 8, for example. Minus 1 to the power of n, x plus 2 to the power of n divided by n. This is very similar to the previous case, so you can see the structure of these two are very similar, so I just avoid explaining the details. I'm sure all of you learned it. We need to find the limit of un plus 1 over un, so we have x plus 2 to the power of n plus 1 divided by x plus 2 to the power of n times n over n plus 1. Why didn't I use the minus 1 over minus 1 to the power of n? Because its absolute value, minus 1, disappears. The absolute value kills the minus 1 to the power of n. This should be less than 1, so again n over n plus 1 is 1, we can ignore it. So what we have is that x plus 2, absolute value of that is 1. I skipped a couple of steps because it's very similar to the previous example. Actually, all the examples as you see are very similar. So we can write, again I skipped the details. You can see x should be between -3 and -1. The radius is 1. And the only thing we should check is the series at -1 and -3. So I start at -3. At -3, replace it here. We have sigma from 1 to infinity of -1 to the power of n times -1 to the power of n. When it's positive, when n is even, -1 to the power of an even thing is 1. So we have 1 times 1. And when n is odd, we have -1 times -1, which is again 1. So this is always 1 over n, which is a divergent series. It's harmonic series, it's divergent. And then at the other end of the interval, at -1, so just replace -1 here. So this is -1. So -1 plus 2 would be 1. So 1 to the power of n, the right bracket is always 1. So the series becomes -1 to the power of n over n, which this is alternating harmonic series, and it's conditionally convergent. So from this is the interval of convergence from -3 to -1. So at -1 it is convergent. However, it is absolutely convergent here. So this is absolute convergence. And then at x equals -1, we have conditional convergence. Okay, so you got it, you learned it. It's very easy. I think since all the examples are the same, that's enough for this part. I had prepared a few more examples, but I think you got the idea. It's very simple. I solved one more. I solved question 27 from your assignment. Or let me solve another one which has factorial. So I solved 26. Solve question 26 from your assignment 9. This one has factorial, so might look a little bit different, which actually is not. They're all very easy. You just do the ratio test and you check the endpoints. N factorial x minus 4 to the power of n. I repeat, it's n factorial times x minus 4 to the power of n. So let's see what we should do. We do again the ratio test. Here I write the ratio test again. Limit of un plus 1 over un divided by 1. It's limit of okay, we have n plus 1 factorial over n factorial, and then we have x minus 4. Let me write it clear. X minus 4 to the power of n plus 1 over x minus 4 to the power of n. This thing should be less than 1 in order for this series to be convergence. So let's see what we have here. This is cancelled with this, and what we get is n plus 1, because previously we saw that n plus 1 factorial is actually n plus 1 times n factorial. N factorial is cancelled with the denominator, so in the numerator we have n plus 1. And then from this we can cancel these two like before. Remaining is x minus 4. So let's see, this is an interesting case. We have limit of, or maybe let me write the absolute value first. So we have absolute value of x minus 4. This is very obvious. This thing comes out of the absolute value, and we have absolute value of x minus 4. The only thing which is dependent of n, and therefore the limit n going to infinity has effect on, is n plus 1. This must be less than 1. However, as you can see, this thing is becoming bigger and bigger, and the limit at infinity is infinity, so it's never less than 1, except at one point. Do you remember the discussion we had in class? This x minus 4 is 0, doesn't approach to 0, is exactly 0 when x is 4. So at x equals 4, we have 0 times something which becomes very big. 0 times everything is 0. Therefore, this thing converges only at x equals 4. This inequality is true only at x equals 4. What does that mean? It means the radius of convergence is 0. There is no interval. There is just one point of convergence, and that's 4. The radius is 0. We have absolute convergence. We have absolute convergence at x equals 4, and everywhere else it's diverging. Again, I repeat what I said about this limit and how this is 0. Pay attention, the limit is not on x. So at x equals 4, the term on the left, this term, is absolutely 0. It's not limit of x going to 4. We assume x is exactly 4. However, on the right side we have infinity. It doesn't matter. 0 times any number is 0. What the case that you had previously, which you said 0 times infinity is not known, it was that 0 was not exactly 0. It was a very tiny number. For example, if you had limit of 1 over n times n plus 1, then this 1 over n when n goes to infinity is not 0. It's a very tiny number that when multiplied by this very big number becomes something, in this case 1. But generally, when you have a tiny number times infinity, you don't know what's happening. You don't know the limit. You should do the L'Hopital rule or any other method you know. But in the case of this example, x is exactly 4. So we have 0 times a big number, and it's 0. That's why this thing converges only at x equals 4 and diverges anywhere else. Thank you very much. If you have any questions, let me know. You have my Skype ID. You can message me there. You can email me there. You can call me on Skype, and we will be in touch. Stay safe from COVID-19. I hope to see all of you very soon. Thank you very much.